Welcome back. There's one more technique that's useful when you have overlapping sets, and that's called the principle of inclusion-exclusion, PIE. And it says that there is a predictable relationship between the union of sets and the sets themselves. Let's look at the union of two sets. If we want to know how many things are in the union of set A and set B, what we can do is we can count everything that's in set A and we can count everything that's in set B and add those two numbers together, but you'll notice that we've counted the intersection twice. So if we subtract off the intersection of A and B, then that will give us the right answer. So again, what we've done here, add in everything from set A, everything from set B, but now we've added too much, and we get rid of everything that's in the intersection, and that means we've counted everything in the union exactly once. Let's extend that to 3 sets. Let's say we're trying to figure out how big is the union of A, B, and C. What we can do is count everything that's in the set A, and then we count everything that's in the set B, and then we count everything that's in the set C. We've overcounted everything that's in both A and B, and we've overcounted everything that's in both A and C. And we've overcounted everything that's in B and C. However, by subtracting out all of those intersections, we've now undercounted everything that's in the three-way intersection. So we need to add that back in. With markers, when we add in A, we've added everything that's in these regions exactly once. When we add in B, we've added everything that's in these regions exactly once. And when we add in C, we add in everything in each of these regions exactly once. So now when we take away A intersect B, we take away one of these and one of these. When we take away A intersects C, we take away one of these and one of these. And when we take away B intersects C, we take away one of these and one of these. That leaves us with 1 in every region except the middle region, and so we need to add that back in. Once we do that, we've counted every single region in the union exactly once. Let's practice using the principle of inclusion-exclusion. Here's an example. How many integers between 1 and 100 are divisible by at least one of 3, 4, or 5? First, why should we expect to use the principle of inclusion-exclusion? As we analyze this question, we see that the universe is integers from 1 to 100, and there are 3 sets. There's a set A, integers that are multiples of 3. There's a set B, integers that are multiples of 4, and there's a set C of integers that are multiples of 5. Furthermore, these sets interact. It's possible to be a multiple of 3 and a multiple of 4. And last, what's the question asking? It's asking for integers that are in A or B or C, which is the union of A, B, and C. And so this question is calling out for the principle of inclusion-exclusion. Now we're going to have to find the sizes of every single intersection. We'll need to know how many elements there are in A, how many there are in B, how many there are in C, but also how many elements does A intersect B have? How many elements does A intersect C have? How many elements does B intersect C have? And last, we also need to know how many integers there are in the three-way intersection A intersect B intersect C. So we have to use some counting technique to figure that out. As we explore this problem, we realize that we need to be able to answer a question that says, how many integers between 1 and some number are multiples of some other number? So let's try to answer this question for all n and all k. Here's the scenario. Let's start writing out the numbers from 1 to 100. As we write down these numbers, we go 1, 2, 3 up to k. K plus 1, k plus 2 up to 2k. How many of these integers in these ranges are multiples of k? Starting at 1, all the way up to k minus 1, there are no multiples of k. But as soon as we hit the number k, there's one multiple of k. And then starting at k, and going all the way up to 2k minus 1, there's exactly one multiple of k, the number k itself. But as soon as we hit 2k, there are now two multiples of k and 2k. Similarly, starting at 2k and going up to 3k minus 1, there's exactly two multiples of k less than n. But as soon as we hit 3k, there's 3 multiples. What we see is a formula for how many multiples of k there are between 1 and n is we take capital N we divide by k and round down. This has a name, it's called the floor function, and we can see that this starts to make sense. If we look at how many multiples of 3 there are less than or equal to 100, well, 3 is a multiple, 6 is a multiple, 9 is a multiple, all the way up to 99, which is a total of 33 different multiples of 3. 100 divided by 3 is 33.3333, and when we take the floor of that number, we get 33 exactly. Let's apply this to the other sets. How many multiples of 4 are there between 1 and 100? It's the floor of 100 divided by 4, which is 25. What happens when we divide by 5? We get exactly 20. And now let's look at the intersections. What does it mean to be a multiple of 3 and a multiple 4 at the same time? Those are exactly the multiples of 12. And so how many multiples of 12 are there between 1 and 100? 100 divided by 12. The floor of 100 divided by 12 is equal to 8. Similarly, the multiples of both 3 and 5 are the multiples of 15. Floor of 100 divided by 15 is 6. And the intersection of B and C are going to be the multiples of 4 and 5, which are the multiples of 20. 100 divided by 20, we know that number is 5. And last, what numbers are multiples of 3, 4, and 5? That's the same as the multiples of 60. There's only one of those between 1 and 100. So let's now answer the question. How many multiples of 3, 4, or 5 are there between 1 and 100? The answer is 33 plus 25 plus 20 minus 8 minus 6 minus 5 plus 1, which is 60. So that's an example of how a question involving the principle of inclusion and exclusion works. Let's talk about one more example that uses both the principle of inclusion and exclusion and the principle of counting the complement. How many binary words of length 12 are there that neither start with 000 nor end with 11? Just like in our previous questions, we need to figure out what the universe is. Every single object that we're counting is a binary word of length 12, and so that's our universe. What are the restrictions on that set? One restriction is that words can start with 000. Another restriction is that words can end with 11. The question wants words in the universe that are not in A and not in B. In other words, we want the set of all binary words that are not those that start with 000 or end with 11. And if you look at this, A union B, that's a clear case for using the principle of inclusion-exclusion. We then recognize that the number of words in this set is going to be the number of words in the universe minus the number of words in the union, for which we can apply the principle of inclusion-exclusion and get this formula. Each of these sets is easy to count. First, how many binary words are there of length 12? There's 2 choices for each of the characters, and there's 12 positions for the characters. So it's 2 to the 12th. What about words that start with 000? Put the zeros in the first 3 positions, and there's 9 more positions that are free. So that will give us 2 to the 9th different words that start with 000. Similarly, how many words end with 11? We filled up the last 2 slots, so there are 10 more slots to fill with zeros or ones. So there's 2 to the 10 words that end with 11. And lastly, what is the intersection? The intersection are words that have the first property and the second property. That is, words that start with 000 and end with 11. So if our word looks like that, it starts with 3 zeros, it ends with 2 ones, and so there are 7 more positions that are left to be filled. The number of such words is 2 to the 7th. And so we see that the answer to our question is 2 to the 12th minus 2 to the 9th minus 2 to the 10th, and we add back in 2 to the 7th. That's it for this video. See you next time.